Hi, and welcome back to another episode in the C# Practical Funciness series. Today's episode is going to be a little different. I'm not introducing any new functional concepts. Instead, I thought we'd take a practical look at how the Validation.T Applicative Functor that we built in a previous episode could be used in a multi-tenant scenario, specifically for constructing value objects without relying on reflection or hard-coded tenant-specific rules. A bit of context first. In my last multi-tenant 24/7 SPA application, still in production, the application was built in the spirit of DDD, but didn't use value objects or require much business logic. However, it did support tenant-specific field validation, default values and runtime customization of all UI text. All this was driven from metadata stored in database tables and loaded into server-side cache and then pushed to clients at runtime, so updating anything was just a matter of changing values in the database. Now, when it came to validation, we leaned heavily on regular expressions and reflection to dynamically validate any configured property on any object. And while that's sometimes labelled as an anti-pattern, it's worked flawlessly for years, no issues, though to be fair, I am the one who designed it and currently maintains it. Still, I wanted to explore a more principled approach, one that avoids reflection, doesn't hard-code tenant-specific validation rules, uses general-purpose methods to keep the flow visible and clear, applies functional programming practices like purity where possible, and leans on the Validation.T Applicative Functor that we've already built. Also, I wanted it to support rule composition using our and then extension method via configuration. So I thought, let's begin with value objects and see if we can make this kind of validation work cleanly in a multi-tenant setup while respecting the domain model. There was some debate in my head over whether to define plain validator functions and inject tenant metadata, or whether to let each validator dynamically build its logic using configuration, but still appear like a normal method in code. You'll see what I mean in just a minute. To keep this grounded in something more real world, I've organised the solution into domain, application, infrastructure and API projects. Everything follows a standard architect structure, with references pointing inwards towards the domain. It's a bare bones setup, stripped down to only what's needed to explore this idea, no distractions. I genuinely hope that you will download the source code and go through it and share your thoughts. Maybe you've solved this problem in a more elegant or scalable way. If so, I'd love to hear about it, and I'm sure others would too. Alright, let's now do a whistle-stop tour of the code. I'll keep the commentary light because the point of this video isn't just to hear me talk, it's to spark thinking about how a problem like this may be approached using some of the topics covered. First to the solution structure. A somewhat typical setup these days. The domain project where our full name value object lives, an application project that orchestrates interactions with the domain project containing a value object service and builder logic, an infrastructure project for our caching mechanism to house our simulated database fetched validation metadata, an API project for the gateway into the app, and a console project that we can use to make calls into our demo app. I have also created a project that's intended to be shared on both the server and potentially client side, and as such have put as much of the validation related code as I could in this project. When I have time, I will look at using the Validation.T for validating DTOs on both sides of the wire. This layout just helps us enforce boundaries and proves that everything wires together cleanly given the direction of the project references. I've reused the same full name value object that we explored in the earlier Validation.T videos, but this time I've updated the internals of the create methods to demonstrate two different usage models. A standard static create method for non-tenant aware apps, but rather than embedding validation logic directly in the value object, I've moved all the rule definitions into static helpers located in the shared project. These are pure methods with no domain-specific dependencies and contain no references to tenant or domain concepts. Effectively, these function returning methods can be reused by any other object that has the same validation requirements, client or server side, as long as they can reference the shared project. The static internal create method is for tenant-aware apps. This method is designed for more advanced multi-tenant scenarios. Here I accept pre-validated, validated of t arguments. The idea here is for the responsibility of the value object to be that only of its construction, if all the values are valid. Access to this method is restricted, it's internal, so the only way it can be called is through a service that inherits from a base service which is also defined in the domain project. This keeps the construction logic clean and ensures that tenant-specific validation logic lives entirely outside of the domain. The value object service is the orchestrator of our tenant-specific validation metadata. This is what I meant earlier when I talked about trying to preserve the appearance of normal-looking methods while letting them dynamically build validator functions specific to each property and customized by the tenant. So although these validators might be built from config data, they're still just regular func delegates that take a t and return a validated of t by the time we use them, and the flow remains simple, composable and readable. Let's look at the value object validation builder, another static class with pure methods. Each method here follows a simple pattern. It uses the type of operator to get the full name of the object and name of for the property name. Then it uses the provided callback function getConfigs to get the validation rules for that property, which is filtered by the tenant. The resulting config list is then passed into the build validator method. Inside the build validator method, we use link to do most of the work. It loops through the rules and uses the rule type enum to select the correct validator factory, i.e. the regex, length or between validator. Each factory's create partial method is then called. This method bakes in the config data using partial application, so what you get back is a validator function pre-configured with the tenant's metadata. If a property has multiple rules, like both a regex and a length check, we simply compose those functions together using link's aggregate method and our custom and then extension. The result is a single composed validator function for that property, even though it may apply several different rules. Now let's zoom in on one of the actual factories, say the regex validator factory. These factories implement a shared interface, the iValidator factory. Each one exposes a create partial of t method, which builds and returns a function that applies the rule. There's nothing clever in these. The key takeaway is that we're using partial application to apply the config data, so we get back a pre-configured tenant-specific function, only requiring a value that needs validating. This makes the function pure, fully configured and reusable as a first-class function. I also included a length validator factory and a between validator factory, just to round things out and show how flexible the pattern is. In my opinion, the beauty of this approach is that you can build highly customized validation pipelines based on metadata without ever using reflection or putting conditional logic into your domain. And just to really drive home that there's no magic going on here, it's all very simple under the hood. Let's take a quick look at the validation factory provider. This class is registered as a singleton in the DI container. All it does is create a basic dictionary that maps the rule type enum from our configuration metadata to a corresponding validator factory. That's it, No magic, no service location, no reflection, no dynamic invocations, just a dictionary lookup to get the appropriate validator factory. Okay, I think that's enough waffle. As I mentioned earlier, the real point of this video isn't for me to walk you through every line of code. It's to encourage you to download the solution and explore it yourself, so you can form your own objective opinion on the approach. Maybe you've tackled this same problem but took a totally different approach. Share your comments on how it stacked up. Alright, let's look at the console client and run it to see what kind of output we get. Quick spoiler alert. Almost all of the validation rule metadata comes from the fallback tenant all, with just one exception. That exception is the family name rule, which is composed of two validators. One part is overridden with tenant specific metadata, while the other part still uses the shared fallback configuration. That's exactly the flexibility I was aiming for, the ability to tweak just the parts that matter for a given tenant or completely change the rule composition when needed. This is why I refer to the approach as a semi-dynamic solution. The structure remains static and strongly typed, but the behavior is shaped at runtime based on the configuration data. All our console client is going to do is to call the API with three values: title, given name and family name, all used to construct a full name value object. The first call sends valid data for all properties but doesn't include a tenant ID. In this case, the full name is validated using the fallback tenant configuration of all. As a side note, in my multi-tenant apps I never expose the tenant ID client side, as they're resolved entirely server side from the user context. The second call sends an invalid given name, just a single lowercase character. That property uses a single regex based validator, which enforces that the first character must be uppercase, but the overall length must be between 2 and 50 characters. This should result in a validation failure, and we should see the appropriate error message returned. Now the third call is where things get interesting. We send a lowercase d as the family name, and we include the tenant ID of tenant1. That validator is composed of tool rules. A regex rule regarding the formatting for the uppercase character, but a separate rule for the length. But here's the twist. Only the regex rule has the tenant specific metadata for tenant1. The length rule falls back to the shared all configuration. This perfectly demonstrates the semi-dynamic composition mentioned earlier, mixing tenant-specific and fallback rules in a single validator function. In this case, tenant1 just wanted a custom error message for the regex, not a whole new rule set, so we only provided that in the configuration data. Lastly, we send valid data again, but this time through the non-multi-tenant create method using the static hard-coded validators that were shown earlier. Alright, let's run the client and take a look at the output, just to confirm what's happening server side. Now you might not be entirely sold on this approach, and that's fair, but if nothing else, I think you've got to appreciate how partial application and the Validated.T Functor can help you build composable validation rules. Anyway, I hope you found something useful in this episode. As always, feel free to leave feedback, whether it's positive or critical, and I'll do my best to answer any questions raised. If you found the video or source code helpful, please consider liking and subscribing. It really helps the channel to grow and encourages me to keep making content like this. Thanks for watching, and until next time, bye for now.